Hello, everyone. We are a team from Harvard Graduate School of Design participating in the Office Division of the US Solar Decathlon 2021. Our team consists of Andrew Gibbs, a graduate student specializing in real estate, Iris Chen, a graduate architecture student, Quan Ting Chen, specializing in energy and environment, Lara Tongholt, a doctoral student in design, and myself, Kritika Kharbanda, an energy and environment student. We extend our sincere gratitude to Professor Holly Samuelson for her constant support to better the project. We also thank all of our industry partners for their help and input. Now we present to you our design proposal, the Resilient Hub. Resilient Hub, as the name suggests, is a resilient and highly sustainable office building. Our project is located in the dynamic Seaport district of Boston, Massachusetts. The site is located in close proximity to several highly visited landmarks, including Boston's Financial District and South Station, the Seaport World Trade Center, and the Boston Convention and Exhibition Center. The Seaport District has a dynamic history, but it started major development in the boom period of early 2000s, and it continues to develop, since Boston's number of jobs is projected to increase by 22% in the next couple of decades. In 2017, Sasaki Architects re-envisioned the Seaport Master Plan to yield almost 8 million square feet of commercial development. Human-induced climate change will continue to exacerbate global warming in the next couple of decades. Towards the end of this century, Boston will experience a significant increase in the number of days with temperatures greater than 64.4 degrees Fahrenheit. In essence, Boston is expected to change from asterisk climate zone 5 to climate zone 4 or 3 by the year 2100. Climate change will also aggravate natural disasters. The Seaport District is surrounded by the Boston Main Channel and the Massachusetts Bay, and is presently already at the risk of flooding, and that risk will continue to increase in the future. By 2070, the expected flood line will pass the building plot and flood levels can reach up to 3 feet. Given these strengths and their significant impact on building performance, this office building was designed with these future environmental changes in mind. The building's lifetime from 2025 to 2080 or beyond, the projected scenario for this site includes urban development on the eastern and southern side of the plot, a rise in the temperatures of about 4.1 degrees Celsius, and an increased flood risk as time progresses. The site is about half an acre and sits on the southern edge of the new development zone. The proposed building has a setback of 130 feet from its immediate neighbor on the east, providing good opportunity for a shared public space. Our plot is intersected by the Summer Street on the south, the West Service Road exit on the west, and the Congress Street in the north. The building's iconic shape has an intriguing architectural appeal, but above all, form follows function. Our first step in the geometry evolution was to maximize the building's FAR in response to ensure profitable returns. Subsequently, the building was carefully sculpted to enhance the public space and its connection to the building on the lower 3 levels, and increase the building's daylight autonomy. Next, by sloping the roof at a 30-degree angle, the building fully taps into the solar potential. And finally, the solar chimney was added. Like other commercial buildings planned in the area, our project provides public functions on the first 3 floors, including retail and restaurant space, a small library, and a daycare center catering to the needs of the community. The 13th floor above consists of office space of around 230,000 gross square feet. 3 basement levels of project provide parking spaces for bikes and cars. This office building facilitates gender equity in the workplace. Even in the 21st century, women still have inequitable access to the workforce. One of the obstacles preventing more women from taking full-time jobs or taking up higher positions in the workforce is that they are more likely to be the primary caretakers of their children. Therefore, this office building has an on-site daycare facility. In addition to the typical daycare amenities, the space has small nursing rooms that female office employees can use to feed their babies between work. Both the public space surrounding the building and the 3 public floors of the building itself provide a connection between the ground floor, the proposed outdoor plaza, and the elevated Summer Street. Office employees and visitors to the office can access the building at any of the three levels and take the elevator to their office floors.
The building employs three main energy efficiency, comfort, and resiliency strategies. Firstly, an adaptable ETFE pillow facade for thermal regulation. Secondly, a solar chimney for natural ventilation. And lastly, a flood-proof building design. In the event of a flood, the lower floors should remain dry and usable. The first measure of the flood-proof building design consists of pervious surfaces in the landscape surrounding the flood. The soil absorbs the first water approaching the building and delays flooding. When the soil becomes saturated and the flood level rises, a valve is opened and the flood water is allowed to flow into the lowest basement level. The basement has a waterproof surface finish and is able to collect a little over 2 million gallons of flood water. This strategy serves the community by mitigating the flood level in the neighborhood. When the lowest basement level is filled, movable mechanical barriers in the public space will close and form a continuous line of protection with landscape embankments. These barriers were designed to block the 3 feet floor levels that are expected by 2080. This design allows the public space surrounding the building, two basement parking levels, and the retail floors to remain usable during the flood. After the flood, the barriers open again, and water is removed from the basement. Due to the basement's waterproof surface finish, the area will dry quickly and the space can be opened up for parking again. This is a layout of a typical office floor plan. As seen in this representative plan, the most distinguishable feature inside the office building is the set of atria. The atria are positioned at the southern corner of the building to bring more daylight into the office space. Because higher floors inherently receive more daylight than lower floors, the atria become smaller towards the top, so more rentable floor space remains. The Atria raised the daylight autonomy of the workspaces from 56% to about 78%. While the Atria reduced the amount of rentable floor area by about 10%, the additional daylight they brought into the office and the view of greenery will greatly improve the well-being of the employees. Studies have shown that natural daylight boosts employee health and productivity, and views of greenery increase job satisfaction and reduces absenteeism. The atria also provide an indoor communal space. The open-plan, flexible design allows the atria to be used for meetings, large company presentations, and informal social gatherings, such as lunch breaks and office parties. Each atria can be accessed directly from each office floor with a circular staircase. The staircase is attached to a slender tensile structure from curtain steel to allow daylight to pass through.
As we showed earlier, the building volume is optimized to maximum energy generation. Our study revealed that in Boston, PV panel placed at a 30-degree angle due south will have the highest yield. Therefore, we balance the need for rentable floor area with renewable energy production by creating a partially sloped roof. The PV panels on the roof will cover about 37% of the annual energy use. Sustainable office buildings typically use wind-driven cross-ventilation for passive cooling. However, our resilient hub uses a solar chimney for natural ventilation because it can provide a higher air change rate and thus a higher cooling capacity. This is particularly important given the future rising temperatures. The solar chimney is optimally positioned on the southern corner of the building and runs along the 30-degree slope roof. Just like for the photovoltaic roof, this location and orientation allows the chimney to receive the highest amount of solar radiation, which will generate the greatest stack effect. The solar chimney's iconic taper shape is a result of the four divided ventilation zones in the building to avoid backflows. Each zone consists of 2 or 4 floors and uses its own isolated solar chimney sections. Because each zone adds to the total airflow, the solar chimney becomes bigger in size towards the top of the building. Our computational fluid dynamic simulation of the bottom zone shows how air is drawn into the building through windows along the northern facades, then flow through each office floor, moving around the core, gathering in the atrium, and pick up speed when exiting through the solar chimney. Our energy simulation shows that the solar chimney increased the ventilation cooling capacity by up to 21% compared to wind-driven ventilation. Also, with the expected future climate changes, the solar chimney will continue to overperform wind-driven ventilation, which is estimated to reduce the annual building cooling load by about 68%. The solar chimney has a dual function. In addition to provide a natural ventilation, it provides daylight access. While the solar chimney exterior glazing has a high solar heat gain coefficient to harvest heat, its interior glazing with highly insulated glass that could transmit daylight but prevent heat radiation into the space. The solar chimney also increases the daylight autonomy of the office space underneath the slab roof and provides views of the skies. During the hour of the year that natural ventilation isn't an option, an HVAC system will take over. Because the building itself and the solar chimney are already designed to support buoyancy-driven airflow, the HVAC system doesn't need air ducts to move the air around the building. That saves space and allows higher ceilings and more daylight. So instead of a central HVAC system, air is drawn in and preheated or cooled through fresh air intake units on each floor. As the airflow flows through the office space, the temperature will be controlled by a well-planned indoor VRF unit. After passing through the office, atrium, and solar chimney, air is either directly released from the chimney, or the exhaust heat will be circulated back into the system with the enthalpy wheel. The VRF system is also supported by a ground source heat pump, which would reduce the building's energy consumption for heating and cooling by around 60%.
To minimize energy use for heating, cooling, and artificial lighting, the building uses an adaptable ETFE pillow facade system. Compared to glazing, ETFE pillows are more transparent, lightweight, cheaper, and have a lower embodied energy. ETFE facades have therefore been gaining popularity in the past couple of decades, also in smaller scale projects such as offices, schools, and libraries. The pillows incorporate PDMS film with a thin gold surface coating that can tune how much infrared radiation is transmitted. Each pillow is composed of 2 ETFE layers and 1 inner layer of the gold-coated PDMS. By changing the pressure in the pillow chambers, the PDMS film can be strained or relaxed, resulting in a real-time change of the solar heat gain coefficient. The material has a slight gold hue, but provides clear views towards the exterior at any strain. In essence, this system's performance is similar to electrochromic glazing, but with all the benefits of an ETFE facade. The southern facades of this building experience high solar irradiation and a significant change in irradiation throughout the building's lifetime. Therefore, these facades would benefit most from implementation of an adaptable facade that can balance daylight access, heat gain, and shading and respond to the changing environment. When the weather gets cold and indoor space needs heating, the middle layer of the facade is stretched, allowing for higher solar gains and passive heating. In contrast, when the indoor temperature rises due to warm weather or increased indoor occupancy and cooling is required, the middle layer of the facade is flattened to reflect more solar heat. Regulation of the facade is automated. Temperature and irradiation sensors distributed on the exterior of the facade and indoor temperature sensors collect data and send it to a central control system. This central brain calculates the optimal strain of the middle PDMS layer and sends instructions to the valves that regulate air pressure in the pillows. Each pillow or small group of pillows can be individually regulated and optimized for smaller thermal zones in the building. Building energy simulations have shown us that the adaptable facade reduces the cooling and heating load in the thermal zones with this facade by up to 44%, compared to a curtain wall facade with tinted low-E glazing, while admitting a similar amount of daylight. This real-time responsiveness will also allow the facade to adapt to global warming and urban development around the plot. The north-facing facades receive significantly less irradiation. Therefore, while the south-facing facades have full coverage integrated solar shading, the north-facing facades require only partial shading. In addition, because the northern facades play a smaller role in daylight access, the window-to-wall ratio of the northern facades was reduced to 40% to reduce energy use for heating and cooling. The geometry of the shading and the number of shades varies for each facade orientation depending on its solar conditions. The northern facades consist of triple-pane low-E glazing and walls from cross-laminated timber, wood fiber insulation, and vertical western red cladding. Lightweight ETFE exterior solar shading with integrated photovoltaics are mounted to a lightweight aluminum frame spanning across the facade. The shades reduce the energy consumption for heating and cooling in the thermal zones with this facade by about 28%. The photovoltaic cells will generate enough electricity to cover about 14% of the building's energy use.
Office tenants desire flexibility of interior configurations. For this purpose, we designed a new type of movable partition that facilitates flexible office use. Each partition has a planter and storage space and sits on wheels so it can easily be moved. The partitions can create a more defined office layout. By adding a glass panel to each partition, they can also create enclosed meeting rooms. Made with an aluminum frame and wooden panels, the partitions give a natural and warm feel to the space. They can be used to provide smaller nooks in large open office space and provide some privacy and an acoustic buffer around desks. The plants also purify air and boost employee health and well-being. The species of the plants can be carefully selected to let daylight through, but still have the desired benefits for occupant experience. To create this open office plants, but keep the structure's embodied energy low, the building is constructed from steel columns and beams with cross-laminated timber floor slabs and a wooden core. These materials reduce the embodied carbon by about 55% compared to structures from steel and concrete. There's often a trade-off between the facade's embodied energy and their effect on building operational energy. However, the facades selected for Resilient Hub reduced both. Life cycle analysis studies for the building envelope showed that due to the selection of ETF and wood, the facade's embodied carbon is about 28% lower than that of a typical curtain wall facade. This design sequence shows how each major design component of this building has contributed to either a significant reduction in energy for heating and cooling or an increase in daylight autonomy. The solar chimney, ground source heat pump, and facade selection significantly reduce the building's energy consumption for heating and cooling. The building geometry and Atria reduce energy consumption for artificial lighting, implying an increase in daylight autonomy. As a result, the building achieved an annual energy use of 31 kilowatt hours per square meter or 10 kBTUs per square foot. About 50% of the building's energy use is covered with renewable energy generation on the roof and facades. Over the course of the building's lifetime, energy use will increase due to rising temperatures and urbanization, but the solar chimney and adaptable facade will mitigate these increases. Most of the design strategies and building systems of Resilient Hub increase construction costs compared to a typical office building. However, the flood-proof design reduces repair costs after a flood, and the solar chimney, ground source heat pump, and facade systems reduce utility costs. Due to the reduction in utility costs, the landlord is able to increase rents, which raises the value of the property. In total, roughly 60% of the increases in construction costs will be offset by the incremental value gain. As a result, our pro forma financial statement showed that Resilient Hub would generate a 21.7% levered internal rate of return. This proved that despite higher construction costs than a typical office building, Resilient Hub is still an attractive investment opportunity and thus financially feasible. Resilient Hub is pushing the boundaries of what's considered conventional office building design. Challenging the status quo with innovative design and technologies is essential to make our buildings resilient to future challenges they will face. Therefore, we hope Resilient Hub will serve as a proxy for future environmentally friendly building designs.